Hey, this is Mr. Mitchell with another video. I'm in the public library, so I'm going to try not to make it too loud. But anyway, here are the questions, and we're going to talk about machines. Machines help people do work. Now, they don't decrease the amount of work, they just change the way it's done. So when we're talking this formula here, whether you use a big machine like this or whether you use a simple machine like an inclined plane, the work stays the same as if you didn't use the machine. What's going to change is somewhere amongst the force and the direction. Now, what usually happens is that you usually give up some distance. Now, I said direction, it's actually distance. You usually give up some distance so the force, make it a lot bigger distance so it's less force, but it ends up being the same amount of work. I'll show you an example of that. Now, here's a crude example of an inclined plane. This is a mountain. Say you have this guy who is climbing the mountain the hard way. I mean, he's going straight up the mountain. But then you have this guy who is climbing it up the easy way. Now, what's happening here? This mountain is kind of like an inclined plane. So the distance is going to be a lot farther as you go up through here than the distance is here. So as a result, that means you have less force. This person's not going to be near as sweaty as this person down here is. So that's exactly what happens when you have a machine. You almost always are going to have a longer distance. And as a result of having more distance, that means you exert less force. And after all, that's the purpose of a machine anyway, that you exert less force and get the same thing done. Now let's look at some examples of machines here. Here we have this guy raising a flag. Now this is a pulley system. So instead of pushing it up, the pulley system allows him to pull the rope down. Now you're going to find out that there is a significant mechanical advantage thing that's going on here, and I'll talk about it here in just a second. But we also have a doorknob. Now this doorknob makes it a lot easier to turn the shaft that is in here. What you have is this apparatus here that is connected to a long, I guess you'd call it a shaft. It is kind of like a stick-like looking thing. But if you were to just grab the tiny stick-like looking thing and try to turn it, it wouldn't be near as easy as grabbing this larger doorknob and turning it. In fact, the larger doorknob you have, the easier it is. Now what you're doing, of course, is you're increasing the distance. You're increasing the distance for less force. So that's exactly the purpose what a machine is. Okay, here we have this lady who is raking. Now this lady who is raking here is putting an input force onto the rake. So the force that she is using in her hands is the input force, the force exerted onto this rake or the machine. Let me go with a different color here. The output force is the force that machine, which is the rake, is exerting on these leaves. So naturally, it's easier for her to put that amount of force there to get the results here than getting down on your hands and knees and pulling them together all at once. So this is going to bring us to the mechanical advantage. Mechanical advantage kind of shows you how effective a machine is. So if you take the output force, that's what's going on with the rake, over the input force, that's what's going on with your effort, then you have mechanical advantage. Now, if it's a good machine, you almost always have an advantage of more than one. If the mechanical advantage were less than one, then it wouldn't be worth having the machine anyway, because it would be easier for you to put forth the effort than to go through the machine to put forth the effort. Now, I mentioned here that you're doing something different with this flag. The mechanical advantage of a pulley system, or at least with the one pulley here, is going to be 1, because he's putting the same effort he would have in going up with it, but going down with it is just a lot easier. So he's not exchanging the distance for anything. He doesn't really have much of an advantage, except it's easier to pull down than it is to push up. Now, there's another term that we're going to call efficiency, and it's going to be down here, and we'll talk about it in just a second. But let's talk a little bit more about mechanical advantage. Let's calculate one. I'll go straight to this diagram here. This person here, or these two people, are using this big log to try to get their vehicle out of the mud. The vehicle is 2,100 newtons. The force they're pushing down is 700 newtons. So sometimes people forget which is the input and which is the output. If it's any kind of machine, the big number is going to be on top. So in this case, the big number is 2,100. Pardon me, I don't happen to have the tablet with me that draws, so it'll be a little bit more laborious, I guess you might say. Over, see, what does it say here? 700. That's quite a line I have written there. Over 700. So if you'd reduce that down, that looks like the efficiency would be 3. Not the efficiency, but the mechanical advantage. Now, you may wonder what unit mechanical advantage is in. It is not in any unit. You just say the mechanical advantage is 3 or 7 or 1 or whatever it is there. Now, look down here. Here we have a similar formula in something called efficiency. Let me tell you what efficiency is first. The machine's efficiency is the ratio of output work to input work. Now, what efficiency is the effectiveness of the machine. And that's a little bit different from mechanical advantage. Mechanical advantage shows the advantage of having a machine in the first place. But efficiency is how effective those machines are. So let's kind of see what we have over here. This is going to be times 100. I don't know why it didn't have it here, but it's going to be times 100. So efficiency is going to be a percentage. And of course, the most efficient machine would be 100%, but you see from this diagram, there are no 100% efficient machines. We live in an imperfect world. We do not have machines with efficiency of 100, but you can see that a bicycle looks like it's 90%. That an electric motor is pretty high also, but once you get past those, we have some really low efficiencies. A diesel engine is 40%. Now, these are machines we use all the time. Diesel engines, steam turbines, they've even got down to the steam engine, which is way down there like 10%. You just are not going to get anywhere close to 100% efficiency in many of the machines that we use. So let's see what this says. We have, looks like a problem here. The stage crew member does 750 joules of work on the pulley. The pulley does 600 joules of the work. Now, one thing to remember, efficiency, you're not going to have the big number at the top of the fraction. The big number is going to be at the bottom. Now remember, that's opposite of mechanical advantage. Mechanical advantage, the big number is at the top. So if you kind of get lost as to what the input and output is on efficiency, big number at the bottom. So let's have 600 joules over 750. So let's see what that is. 600 over 750. Working on this. 600 over 750. Wonder why my calculator's not working very well. Oh well, I'll just go back 600 over 750. That's probably something around 85%. And it will be a percentage. So efficiency is a percentage, and this is quite a pretty good efficiency. Oh, let's see what else there is here. Oh yeah, one way to make, oh my bad, I skipped ahead in my notes. The effectiveness of machine, okay, oh my bad, I've got it here. Machines sometimes lose efficiency to heat. And you probably have noticed that if you ride in a car a long time and put your hand on the hood, it's hot. If you use your computer a long time, you put your hand on the computer, it's hot. That is efficiency that has lost. It's friction is all it is. It's friction. And you have machines like engines who have pistons going up and down. You have to have something to try to reduce the friction. So what people use in their engines is oil to try to reduce the friction. And the oil makes it, well, in fact, you just can't run a car without oil because of the friction will really make it overheat. But that applies to something more than just mechanical machines. It applies to like bicycles. Take a look at this bicycle. You have the chain, which has kind of gone down a little bit. You probably haven't had oil on this chain in forever, and doesn't even have a wheel on the front. Looks like the rubber is on the back, but not on the front here. So if you were to try to take this machine out, its inefficiencies would probably make its a very low percentage. And even a bicycle here, which is probably well oiled, I mean, look at the surface here. You're going to have these rocks here, and you're going uphill. This is a mountain biker. You're just not going to have the efficiency that you would have for like an Olympic bicyclist. Look here, trying to reduce air drag by having a specialized helmet. I'm pretty sure these kinds of wheels with the solid interior are to try to reduce air resistance. Probably very well oiled bicycle and chain. This guy is leaning down to try to reduce the air resistance, and probably going to have a very small percentage there. Well, I hope you've learned a little bit about machines, efficiency, and mechanical advantage.